All right, here we go. CCNA3, Chapter 5. I know you guys already read this. Plus, you've read it before, right? So it was super interesting. So you hit every aspect of it, I'm sure. But anyways, we're going to go over it anyhow. And what is it about? Single area OSPF and adjusting it. Pretty much everything we've done before. Maybe we didn't do the securing routing updates, but everything else should be a review. And with that, we'll go. Oh, actually, we'll go over this. Modify the OSPF interface priority to influence the DR and BDR election. Configure a router to propagate a default route in OSPF network. Modify OSPF interfaces to improve network performance. Configure OSPF authentication to ensure secure routing updates. Explain the process and tools used to troubleshoot a single area OSPF network. Troubleshooting and missing routing entries in single area OSPF version 2 route table. Troubleshoot missing route entries in a single OSPF version 3 route table. Alright, here we go. Routing in the distribution and core, which is where routing happens, right? We're going to aggregate in the distribution core, and so we can do routing in two ways, but you guys already know this. Once again, review manually, which would be static routing. Holy cow, and this network, it probably wouldn't be very much fun, especially when we get this core up here. Yeah, if we're routing up here, right, so like all of this is probably layer 2, but you know, maybe we're going in, I mean, we're probably layer 2 right here too, and everything going down, and so yeah, we could route, but we're routing in between from here to here somehow until we go into the core, and then wow, okay, so we have these redundant links, probably a VSS virtual switching stack going on right there, and so I guess that's not that many routes going on, you know, just the internet, the firewalls, and all that. But if we want all these default routes up here to be learned down here and fed in, yeah, we're going to do that dynamically probably through something called EIGRP, which we haven't gone over yet, but we have OSPF, open shortest path first, right? And that's what this chapter is about. So, advanced single area OSPF configurations. So that's what we have going on right here. I really wouldn't call this one an advanced one, but oh, we just have static and default route scenarios, right? Two routers. Oh, that's easy. We just put a default route that way, default route that way, a static route to here, a static route to here, a static route to this one and this one. I know you guys saw that those are different networks because they are different router interfaces, or just look at their IP mask. Right? We have 4 networks. And then I guess we have 5, but that's just going to be a default route from each one. IP route 000 out this interface, or to the next hop of here if I am this guy, or 000 to out this interface, or to the next hop of this guy. And anyways, that's our default routes, whereas we would actually put a static route in for here, IP route, whatever the network is, and how we get there, which would be probably out here, or like here we would, no, actually we wouldn't have to, I take that back, we only need the default route. Must be getting rusty. Anyway, so default route Y, these are directly connected, so it knows everything over here, right? We know these directly connected routes, this router knows these directly connected routes, but it doesn't know how to get here, and this guy doesn't know how to get here. So, sorry about the lies. Try not to do it again. Alright, so actually there are some good things about this. Ease in the routing table, right? If you don't have very big routing tables, fine. Routing into from stub networks is easy with the default route, static default route. Using single default route, you know, we only put one route here, and it works. Probably easier than dynamic routing. But we go to dynamic routing. Why? Well, I don't know, they gave you the same one, but I guess you just put in these networks and they'll work, and instead of relying on a default route that could go down, you could just put in no default routes at this point, and it would find everybody in this area. Oh, and because we'd put a default route out to the internet, and so I don't think we had that in the last one. I guess we'd default route out there. We'd actually have to program in here. Once again, I'm all messed up on here, so I guess we'd program in 3 routes, right? We'd have a default route to the internet, and then right here we would put in these guys that it doesn't know, and on this router we'd put in these guys it doesn't know, and default. Actually, I take it back again. Alright, this is the final one. This is the final one. This guy could have a default route because the default route is over here. Okay, so if it's not over here, everything else is over here. So this guy could have a default route, but this one would need a network to know where this network was and this network was, and then feed everything else to the internet. Okay, thank goodness we got that all solved. Alright, so now I see the internet in this one. We would feed the default route out of this guy through OSPF to everyone else, and all the other networks would be learned dynamically. We wouldn't have to worry about it, but this network would come out and we'd be happy because it'd be easier than our last one, and we wouldn't have to think about it because, I mean, I can't even figure out what's going on until the 3rd try. Anyways, here we go. So that's what's great about dynamic routing protocols. You guys kind of remember that, hopefully. So what are some features of OSPF? Well, it's classless, and if you guys remember what that means, is it doesn't have classable boundaries. It is always classless. EIGRP can be both, whereas OSPF is going to be classless. We're always putting that subnet of that network in a routing table. When we do a network whatever, it has that wildcard mask that's going to go in there. Hopefully you guys remember that. It's efficient. Why is it efficient? Remember, compared to RIP, it is the greatest thing ever. It only uses resources when it starts up, builds all those routes, and then it's just sending little tiny hello packets to make it hello. What do they say about it? Routing changes trigger routing updates, no periodic updates, right? So if it's not changing, all we're getting is little tiny hello packets. Fast convergence. Well, whenever we say advanced, probably what it's saying is we want it to converge faster. So if something goes down, we want it to converge faster. And fast convergence means 1 to 3 seconds, typically, when we're talking about EIGRP or OSPF, is that we could have that back up and running within 1 to 3 seconds of it being down. Hopefully nobody would notice. Scalable. Well, OSPF as a single area probably not the best to scale or to converge or anything, but we can make it and then secure. Our routing updates, not our traffic, but our routing updates to get in there, we can password protect it with MD5 if we want to, so that somebody couldn't just get on there and say, oh, there is a password on OSPF, and in clear text I'm going to look at that same password, become part of OSPF, and do what I want with your routing protocol. Alright, so routing in the distribution core. I don't know. No, configuring single area OSPF. Sorry, looked at the main title. Well, as you can see, we're setting router IDs, and they're all in area 0. And I know you guys remember area 0 is the backbone area where everybody sets. So probably if we're doing a single area OSPF, we're going to have an area 0. Definitely we're going to have an area 0 if we have multi-area OSPF, which is the next chapter. But remember, the router ID tells us who the DR is. And remember, through spanning tree, we were here, spanning tree, right? And spanning tree said, hey, I like the lowest, alright? I like the lowest to be the boss, which was our root bridge had the lowest MAC address, or the lowest priority, or the lowest whatever. Spanning tree, the DR, remember, is going to be the highest RID, or the highest, first we have, what are we going to use? We're going to use the physical IP, right? Then we have the loopback. We don't have a loopback on here, is what it's going to pick up to build that router ID. Then the actual programmed router ID. And then finally, I think we can actually program a priority that goes even higher than that. We'll find it as we go, but probably we're just going to use this router ID, most common to use. So this is the DR in here. This is the BDR, backup designated router and designated router. Remember, designated router is the boss. Backup designated router is going going to come in if that doesn't work. If you guys can't remember some of these commands, actually this one is kind of important. This is going to change that cost. Remember, OSPF was designed for slower networks, so that if we had a 10 gig link, it looks the same as a 1 gig link or a 100 meg link. So we want to set that, and actually if we had 10 gig, we'd probably add another 0 onto that to calculate the cost, right? This is calculating it for 1 gig speeds. Auto cost reference. So this is where we build our cost based on the correct bandwidth rather than 100 meg is the highest we go, because if we keep it default without this command, 100 meg looks the same, 1 gig looks the same, 10 gig looks the same, or 40 gig even if we were going up that high. Probably not going to the routers. Yeah, router ID. That's how we set the router ID, right? Router ID. We're in router OSPF 10. Hopefully you guys have these commands written down. Remember them. For some reason, these guys did program a command of, router. Let's see what do we have? A gig link here. So they want it calculated. Remember, the bandwidth command is useless. It is useless. The only thing it's used for is cost and EIGRP or OSPF. It does not actually set a speed. It says, hey, on a routing protocol, this is what you're going to program as. So that's what that's doing. Auto cost, passive interface. This is going to not spread updates. If we go back and look at our picture right here, where are we going to put our passive interfaces? Well, this is probably all switches down here. Switches don't need routing information unless they're a multi-layer switch. So we want routing information to go here and here, right? Passive interface says, hey, no hellos are going to be here. We can't form any adjacencies out here. We don't want a passive interface here because then we can't get any neighbors from anything that's coming through there. And so go back. And 3, what's it showing us? Same thing, how they set up 2. Now, if you want to try those commands, you have an option to do that. I think we've issued all those commands before. If not, this is your chance. So, how do we verify? Here's our show commands for OSPF, right? So show IP OSPF neighbors. Another review, right? So this is actually going to be our router ID. Right? Neighbor ID, that's the router ID of the neighbor. The priority, the state it's in. So now, if this wasn't in full state means it's fully converged, right? If that was stuck in loading or something like that, as we'll probably go over here in a little bit, it means that we probably don't have routing going on. We found the neighbors, but we did not get full convergence on that, or the Dijkstra algorithm didn't complete. Alright, so our dead time, remember we can set this to kill the route out of there. It should be here in a second. We have on the show IP, we have their actual the IP addresses of our neighbor device. Remember, this is the OSP router ID, not the actual IP address. This is the IP address of that's connecting those routers together in the network. And this is our interface that they're going out of, right? Probably could figure that one out. So let's see what our next show command is. Show IP protocols. Okay, so what is it showing? Well, we get router ID and maximum pass. If we were going to have, if we had perfect cost, we could load balance on this. That kind of thing. What are we routing for? What is our dynamic routes picking up? Where our passive interface is at, and then once again we get these router IDs of our neighbors, and actually it's given us the cost here too. Alright, and our next one, show IP OSPF. So this is going to be for IP version 4, right? Because we know IP means IP version 4, and we get our number of areas, and some advanced stuff that we don't really need to talk about yet. Let's see what it says. Command is used to display OSPF process ID and router ID, as well as OSPF shortest path first and OSPF area information. We'll talk about some of these LSAs in a second and that kind of thing. It says, well, it says we're in the backbone area. Yeah, so don't know. Might have to use that sometime. Show IP OSPF interface. Just going to read that one too because it's got a lot of stuff. Command provides a detailed list for every OSPF enabled interface and is very useful to determine whether the network statements were correctly composed. Show IP OSPF neighbor brief. It's going to give us similar stuff, except it's a summary, right? So less stuff to look at. What interface are we at? What's the IP? This interface is actually a DR. Yeah. These ones are just point to point. The difference is, and maybe you guys remember this, so what this means DR, why there's not a DR on these are serial, so they're point to point links. So no Dijkstra algorithm here, no OSPF, they don't actually elect a DR and a BDR. But on our gig interfaces, on our shared multi-access, we are going to elect them, right? Okay. Oh, what else do we have? 6. Oh, there's your display if you really want to do it. Those are important though. You really probably want to pay attention to those commands because I'm sure there's a drag and drop based on all of those commands on your test. Alright, so now we have OSPF version 3, meaning what? Oh, what are these IP addresses? Everybody's favorite, IP version 6. Okay, so version 3 is for IP version 6. What are we noticing? Well, for some reason, we haven't set a router ID yet, which we do program these differently, and I think most of you guys got this working. So what it is, so first, we do the same thing as always. We do IP version 6 router OSPF 10. All we're doing is setting a router ID. Okay, so we set a router ID because it cannot build a self-built router ID otherwise. Why they're not showing that router ID on here, I don't know. So that's what we're going to do there. Build that router ID. They set their auto cost for reference, so we have the right speeds again. And then instead of programming networks, we go back into the interface. As you see, they go into the interfaces that are actually being programmed. This is the difference between IP version 6. And they just say IP version 6 OSPF 10 area 0. Why don't they have to put in the network? The network's always already programmed on the interface, so it knows it's just going to start sending out stuff here, right? It's going to start sending stuff out after we say, hey, yep, you're in this OSPF area, send it out. See the other side? Feel free to program them. We will find out why they are sending, why they have the link local here in a second, as we talk about OSPF for version 3. Alright, so our IP version 6 neighbor commands, all the same command, or show commands, basically all the same commands, just put IP version 6 instead of IP in front of them. Feel free to try those out. Alright, so now we get into our fun stuff. Like I said before, where do we not have a Dijkstra algorithm? If we're doing point to point, right? So point to point, why do we not need a BDR and a DR? There's no options. You're either the DR or you're not. Alright, so then we go to point to point. Here we're actually, or multi-access network, right? And this is a broadcast multi-access. What does that mean? It means we're going over Ethernet and we have these high bandwidths where we still can have broadcasts. And so this is going to have a different dead time, right, by default. Maybe you guys remember that. Then our next one, which is non-broadcast multi-access. So if we go to non-broadcast multi-access, it's something like frame relay, which you guys will learn about in CCNA3. And basically, it's going over these serials, and frame relay is slow. We're talking usually in the KB. So probably not something likely you're going to see, but it forms these virtual tunnels where we separate out. See, these are T1s probably, right? So we have our serial T1s, and we can separate those out into slower costs, so we don't have to pay for the full T1. So one T1 can actually go to two places. So we have virtual links going here and here. So this is non-broadcast multi-access because it virtualizes point-to-points over this frame relay cloud. So here's a point-to-multi-point network frame relay, but two are going instead of just using the framed another frame to relay thing. We'll learn more about it in OSPF. This used to be a CCNP only, and I don't know why they're putting in our single area one, but it's called a virtual link. And so a virtual link is, remember, all areas have to connect to the backbone area, which you know that because we had to learn it in the last CCNA. But so area 1 could connect to the backbone area and feed into the backbone area. Area 51 could not. And so if Area 51, what it does is we program a virtual link, and basically a virtual link would be like, this is a company next to us in the ISP route, or I don't know, next door that shares a service provider client cloud with us, or we've gotten connected somehow, so they're on this area, and it's just a temporary thing, and it says, hey, form a VL, a virtual link through here, and what that's going to say is, hey, to get to the backbone area, go through area 1 to get there. It is only a temporary solution used for short times, so that's a virtual link. Alright, so we're back to our multi-access layer, and so what does the multi-access layer do? It has creation of multiple adjacencies. Why? It's not point to point. So we have our adjacent to 3 other neighbors, which the bigger our adjacencies, the more flooding it is. That's the bad thing about a single area OSPF, right? So Ethernet's network could potentially interconnect many OSPF routers over a common link. Creating adjacencies with every router is unnecessary and undesirable. This would lead to an excessive number of LSAs exchanged between routers on the same network. And link state routers flood their link state packets when OSPF is initialized, or when there is a change in topology. This flooding can become excessive. So the more adjacencies we get, the worse our performance is. And maybe you guys remember this algorithm right here, how to calculate adjacencies. So we say n for the number of adjacencies times n minus 1 divided by 2, and that's how we calculate, or actually n is the number of routers, I'm sorry. So the number of routers minus 1 divided by 2 tells us how many adjacencies we have. Okay, so as you can see, if we took that, we had 4 minus 1, which is what, 3 times 4 equals 12 divided by 2 equals 6. So that's just the algorithm, or the adjacencies in math, and it shows you how the adjacencies scale fast, and so that's why we do multi-area OSPF, is to keep adjacencies down. But I guess that's for tomorrow, right? So establishing adjacencies. So when we're on a multi-access network, we form adjacencies, and how do we do it? All these routers flood their LSAs, and a DR and a BDR is selected, and then when there's a change, this LSA sends, or this router says, hey, here's an LSA, and if you noticed, where did it go? It went to the DR and the BDR, right, which is the backup. Yep, went to both of those guys, and so then just the DR sends to make all the changes, but what it does is it allows the BDR to keep its map of the changes in case the DR was to go down. But the DR is the boss and tells everybody of the changes. So one router sends it there after these adjacencies are all established. But that's how the DR is the boss. Let's see, what else? Remember, the DR is established through highest router ID or highest loopback or finally highest physical address. These are all set. So this is the DR 222 BDR, right? And then this guy is actually, it's on this other one. Alright, so we have the DR and the BDR. What's going to happen? All other non-DDR BDR routers become DR other, a router that is neither a DR nor a BDR, a druther. Okay, what a cool term. Alright, so this guy's the druther, BDR, DR, area 0. So all they're doing here is doing some show commands of how we can see the DR. Feel free to look through those show commands. Because they're just verifying the roles that I just talked about. Alright, so here we go. Show IP OSPF neighbor, state is full. Remember, that means the adjacency went through. And we have a DR and BDR. That was the show IP OSPF neighbors. We could have a full druther. Just talk about what that meant. It means it's not DR BDR. We get a full DR, full BDR, or a two-way druther. I believe this means that it didn't work. The non-DR or BDR router has a neighbor relationship with another non-DR or BDR. These neighbors exchange hello packets. Oh, so I'm wrong. So it's not full loading, but that must happen probably only in a virtual link. Let's see. Oh, I guess I know where that would happen. Let's see. Does it actually give us a show here? It would be where they all still are in the same area, but okay, no, this guy. So we'd have two druthers right here. So this guy would still forward links. Maybe if we had another druther over here, right? They'd be in a two-way state. Alright, so what's next? Default BDR election, we talked about this. Router ID can manually be configured. If there's no router ID configured, it's going to use the highest loopback. If no loopback is configured, it's going to use the highest IP address. Okay? Yeah. So then what happens if the DR fails? Alright. The election process, well, actually, the BDR becomes the DR, and this druther, he doesn't have any competition, so he's the BDR, right? So what happens if that guy comes back up? Let's see if it shows us. Oh, he came back up, but he's still the druther, right? Because we would have to run a whole election process again. So if everybody went down, back up, he'd become the druther again, or we want him to be the druther, because if he has to take over, you know, we're gonna have to reconverge, and wouldn't be a great deal, right? So if we set these router IDs, so now they added a new router, and he has a higher router ID, but he's still the druther because we were already up and running, and so we would actually have to clear the OSPF. Let's see. I can't remember the actual command to get it to go, but it would be clear IP. I don't know, it's at the show command. I'm sure it brings it up. Actually, when you type this in, it gives you the command. Cannot think of it off the top of my head, but it's a clear the I think, IP OSPF process, I believe. You're clearing the OSPF process so it recalculates all this. So if you wanted to recalculate it, you'd do it on downtime and do that. Because as you can see, even though they both came on, this guy becomes the BDR because they just re-elected for that, and he has the highest router ID. This was the BDR, so we already know this table's all built. So remember, as a druther, this table wasn't built. Yep. Anyways, that's what they're showing you there. Alright, so now we have OSPF priority. To set that, we can set that beyond. Right, I think they're talking about actually interface priority. Let me look here. Yeah, no, we're setting interface priority, and so we can set 0 if we have a really old device that we never want to go up, and 1 through 255. The higher the priority value, the more likely it is to become the DR or the BDR. Right, so 255 would say, hey, we really want this to be BDR or the DR. 254 would be a bad. And why we're doing that is this would actually become the highest priority on an interface is going to be used in an area. And why we would do that is if we had multiple areas, say there was another, this was going to be then area 2, A2. Okay. Maybe we don't want this to be the DR for both. Maybe we want it to be the DR here, but not here. So the router ID, we can break it up into different areas and make that have different priorities through this IP OSPF priority command, and it's at the interface level that we're doing that. Probably not something you'll see around this area, but maybe someday. Okay. Oh, here's our changing our priority. So it probably is going to finally give us. So we change that. It would actually give us an area. Change that. And here we go. Clear IP OSPF process. That's the command I was looking for. Until we do that, that's when it's going to change our adjacencies. But whenever we enter those commands in the real world, I think even on Packet Tracer, it tells us that we have to enter that. And so it will make the correct routers, BDRs. But if you want to see how to set the IP OSPF process, there it is for you. Alright, so now we've talked about how we can form adjacencies. Remember, the adjacencies are going to feed all this network information in, and they're going to do it different way between IP version 6 and OSPF, and IP version 4 and IP version 6. IP version 6, you're going to form adjacencies through just putting that you're running in there. We're in IP version 4 here, so we're going to type in the network command, and then the network address. It's 192.168.1.0. Remember, it's a network address, and then we'd say our wildcard 0.0.0.255. Right, 255. And then right after that, we're going to put in our area right here. Right, so area 0 probably if we're doing a backbone area, or if we're doing a single area. So that's how we're putting those networks in, and those are all going to build as long as we have that network command in here and here, and this network here and this one here, and we're going to put that in. So this one feeds, and so this one feeds, and so this one feeds. So now what do we have left over? We have this default route to the internet. Okay, and so this is different from EIGRP. Well, the first thing we're going to do is, I'm sure you guys all remember how IP route and then our static route to the internet, right? 000, 000, and then either the IP address up here or our exit interface is the command there, right? Then inside of OSPF, inside, so we go into router OSPF 1, remember, which is the process ID, or 10, whatever our process ID, router OSPF, or IP router OSPF 10. And once we're inside there, okay, inside there, then we put in default information originate. And what that's going to do is, if we have a default route, it's going to feed that to everybody else. Say, hey, if you want to get the internet, you want to get the default route, come to here. Okay? And that's how that works. And it only works like that. We do default information originate in two protocols, RIP and OSPF. And so what we're going to do is, we see that we statically set that, right? So this would be the router that is connected to the internet, and it's actually, if it was shared, it's going to be an O2 or an O1 with a wildcard. So it should be showing us that somewhere here, but apparently it's not. Okay, so we go to IP version 6, and the reason they're showing these link locals again is our link local address. I said we're going to talk about it. Maybe I missed it. But anyways, I know it was in when we studied originally. It's going to be the where these send. So they send to like FF02, I believe :5. Let's see, FF02. 1 second. Okay, so FF02:5 is all SPF routers, spanning, which is shortest path first routers. And then FF02:6 is going to be all DR routers, which we know FF02 is just a multicast for version 3, but it's going to have the source is going to come from the link local across all of these, and then that multicast to the rest. And then the version 2, if you forgot, what they sent on is 224, or a multicast, right? 224.0.0.5 and .6, which this is to all the people that need updates, and these are updates to the DR. Okay, so how do we set up a default route through IP version 6, a static default route, which IP version 6 just route :/0, right, which is all zeros on IP version 6, and then the IP version 6 address and the exit interface are both, and then default information originate again, so inside of the same place, and that's gonna save a default route. And so this time, is it actually going to show us an OE2? So we'll just do show me. Okay, so this is our default static route is OE2. It should, typically that's going to have a wildcard on it too, just like always, but maybe IP version 6 it doesn't. I've never seen that there. So let's go back to the IP version 4 command and see if it shows that OE2. Yeah, OE2. See, we get a wildcard there. O asterisk E2. Asterisk, remember, means it's a default route, and E2 with OSPF. We can either have E2 or E1s. They mean external routes. One, we actually calculate the path to it. The other one is just set default. But that's CCNP information too, so don't worry about it. Alright. Default route propagation. Fine tuning OSPF interfaces. So we could change our hello and dead timers if we want to be faster. Remember the hello timer, whatever we set this to, if we set the hello timer, the dead timer is going to be 4 times. So you see it's set at 10 seconds, and we could set it to 40. And we do that by, well, they're just doing a show. So if we want the timers to get faster, we can say inside the interface, we can say OSPF hello 5, dead timer 20. Remember, we need to do that on both sides for this to form adjacencies. The hello and dead timers have to be the same in OSPF for them to form an adjacency. And so they want hello timers to go faster. I don't know anyone that does this, but you could if you wanted a faster convergence, I guess. IP version 6, same commands. Alright, so here's the fun stuff. How do we secure it? Secure the routing protocol. So you see we're going over the cloud, and so that's why we want to secure it, because otherwise this guy can man in the middle our entire process. And so also it's just good practice to password about anything, right? So it keeps people from DOSing you, man in the middle you, or doing anything in between, learning false routes. So by default it's null, right? And then we could do simple password authentication, but it doesn't help us in that scenario because it's not going to be encrypted. And then when we do MD5, it's actually MD5 per encryption to keep us a little better, right? So I don't know what they're showing here besides that it's just an encrypted password that needs to match. Alright, so how do we set this up? Well, actually that's what it looks like. So it comes over like that. If our secret keys are the same, we're going to work, right? Either accepts or declines, and then you can become a routing neighbor. So when we first set this up, if you're setting this up on a running network, you want to be very careful. Probably run EIGRP as well, or something in the backbone, because this is going to take you down as soon as you put it on. And yeah, so probably don't want to do downtime. So be careful with this if you're doing this in the lab and put this on, because you'll lose connectivity, which we know because we know our theory very well, that even if we lose connectivity, we can still go from this guy to this guy and this guy to this guy, but not to here unless we put a static route in there. Okay, so we could save it if we needed to. So how we do it is first we build a IP OSPF message digest key, and I usually say OSPF MD5. I just call the key OSPF. And then the password you're going to use. So this sets this secret key that they're talking about, so that needs to be the same on all your devices that are doing this. And then you're telling the area to use the authentication with message digest. And this is from the interface. We're going to put this one in here, serial or wherever we're going. Then this one, we're doing it at router configuration mode, global configuration mode. We're just saying, hey, from now on we're using this area ID, so area 0 authentication message digest. So from then on we got MD5 and our network is a little more secure. If you didn't understand what I was saying, here's this example for you. And how do we see if we have it? We did the show IP OSPF interface, and we're looking for message digest and the key ID. So if you guys should probably, the way that makes the most sense is probably build your own lab and form an adjacency on there. It works in Packet Tracer, so try it there, because it can be a little confusing until you've done the message digest before. But once you get it up, it's just as easy as anything else. But like I said, if you turn it on one, you got to turn it on the all, or you lose all your router adjacencies. So what causes adjacencies to form? Our interfaces have to be in the same network. Do you remember that? OSPF network types do not match. What does that mean? Network types. So actually, I'm not even sure what they mean by network types. I would think that would be like you're sending hellos on this side, but not this side. Like you have an enabled network, this network to form adjacencies, but you have this one. That must be what they mean there. But if you've set these in different networks, like put in your network command wrong, they're not going to form adjacencies there. OSPF hello and dead timers do not match, so we changed this side to make it faster, but not this side. We're not going to form adjacencies. Interface or neighbor is incorrectly configured on passive, so we put passive and maybe default on this router, and so every interface is passive. There's a missing OSPF network command. We forgot to put it in. So I think a lot of those are actually redundant, but hey, that's our typical. Then here's that whole transitioning, which is why I'm still kind of confused. I think when we see that two-way state, it's not a good thing. In my experience, that's when we weren't getting routes. So I would guess if you ever saw a two-way instead of full loading state in your routing table, that's where we see those state. Actually, it says two-way states are normal, but I don't know. I like to see full, but maybe I just haven't paid attention on routers that are way out here. Maybe they're gonna have two-way where this is the DR, okay? Because didn't have enough neighbors. Anyways, so it goes down, init state, two-way state, exchange state start, exchange state, loading state, full state. Typically, you see loading and then full unless you have debugging on. Then you're going to see all of these states come through. They're doing the show commands again. If you'd like to see those, go through them yourself. We've already talked about them. What are some? How do we troubleshoot OSPF? Well, if we look to see if we're missing routes, we check to make sure all of our neighbors are there. We have the correct amount of adjacencies. That we put the network into the routers that we did, and I guess path selection would be if we're forming a loop or something, we would want to troubleshoot that. But what do? Most likely, are the interfaces operational? Do we have MD5 on them? Whatever. Well, you do the show commands. Go ahead and go through this. Because it'll give you where your show commands are. Except for, yeah, I guess right here. Typically, your problems are caused by either passive interface or not be connected to areas 0. They say an ACL blocking them, but yeah, just go through those yourself, because you will probably see them if we have enough labs. And guess what? As you all know, there is an OSPF lab that we will be doing shortly on this OSPF packet tracer. Check the class for that. Be fun. Feel free to do those activities for the troubleshooting if you feel like you need to. All practice is good practice. Alright, and that was single area OSPF. As always, if you have any questions, send me an email or post it on the discussion.